So we'll start the last topic, which is block 5 in atomic physics. It is a short topic, and the first part is about the nucleus and the atom, and the second part is about radioactivity. So everything is made up of small, tiny particles, which we call atoms, and each atom is very small, and the core of the central part of the atom is called a nucleus, and around the nucleus there are particles which are orbiting. We call them as electrons. And proton and neutrons are known as a nucleon, and inside the nucleus it contains proton and neutron. The protons have a positive charge. These are this like information about the atom, whereas neutrons are uncharged. They have the same mass as proton. An atom is electrically neutral. Why? Because it is having equal number of protons and neutrons. So there are protons are positively charged, electrons are negatively charged, and the positive charge balance with the negative charge. That's why the overall atom is neutral. So as you can see here, this is a proton, so there are three protons and there are three electrons. So plus 3 and minus 3. So what is the net charge? The net charge is 0. So atoms are electrically neutral, and the identity of the element is a proton number. Like every element is having a unique proton number. So using a proton number, we can identify the type of the element. As you can see here, the first example, helium is given. There are two protons. So whenever two protons are there in the nucleus, that is always a helium. The second one is a lithium, which is having three protons. And to be an atom, the number of the proton are always equals to number of electrons. So if two protons are there, two electrons. Here lithium is having three protons, so three electrons should be there. First shell it is having two proton, and the second shell it is having, first shell it is having two electron, and the second shell it is having one electron. So for an atom, the number of the proton is equals to number of electrons. How we represent an atom? So we represent an atom by a symbol X, A, and Z. What is A here? That is a nuclide notation. So nuclide is an atom of a particular structure, and each element has a nucleus with a specific number of the proton. So nuclide notation is A, X, and Z. What is A here? A is a nucleon number, or also known as a mass number. Z is a proton number, or also known as the atomic number, and X is a chemical symbol of the element. Example, for carbon it is written 12,6. So what is the nucleon number? Always nucleon number is either equal to or greater than the proton number. So 12 is a nucleon number here. And what is the proton number, or Z? That is 6. If we want to find the number of the neutrons, that is given by a formula A minus Z. So nucleon number minus the proton number will get the number of the neutrons. So nucleon number is 12, proton number or atomic number is 6, so 12 minus 6, so it will have 6 neutrons. How to find the number of the protons? So number of the protons are given by Z. In this example, Z is 6, so that's why 6 proton. And because it's a neutral atom, there is no charge written on this. And if there is no charge, the number of the proton and electron should be equal. So how many electrons will be there? It will have 6 electrons. So you should be able to work out the number of neutron, proton, and electrons for an atom. So if there is another element, like example, lithium is there. Lithium atom is there, which is written 7 and 3. It can be written other way around. They can write as 3 and 7. But always remember, the nucleon number is always greater than or equal to the proton number. So what is A here? When we work out any one of them, so A is 7. What is Z, the atomic number, that is equals to 3. So if you want to find the number of the neutrons are given by a formula A minus Z. So that is equals to 7 minus 3. And 7 minus 3 equals to 4. To get the number of the protons, that is given by Z. So Z is 3. So number of protons are 3. And to find the number of electrons, that is same as a proton because it's a neutral atom. So if 3 protons are there, it should have 3 electrons. So using the nucleon number and the atomic number, we can work out the number of the neutron, protons and electrons inside the atom. So example, if you want to describe the lithium atom, the structure is given. So for a lithium atom or at the atom of a lithium or lithium atom consists of 3 protons and it contains 4 neutrons, and around the nucleus there 3 electrons are revolving or orbiting. The proton number is actually defined as a number of the protons which are present inside the nucleus, and number of electron equal to number of the proton for an element. And identity, to identify the element, we always use a proton number. Whereas nucleon number or the mass number is a sum of neutron and proton inside the nucleus of an atom. Then what are isotopes? Isotopes means they're atom with the same proton number or atomic number, but they have different nucleon number. We call them as isotopes. Example, hydrogen having 3 isotopes: hydrogen 1 1, hydrogen 2 1, and hydrogen 3 1. So when we find the number of the protons, here A is equals to 1, Z is equals to 1. For this one, A is equals to 2, Z is equals to 1. And here A is equals to 3, Z is equals to 1. To get the number of the neutron, that is A minus Z. So when we subtract 1 minus 1, that is 0. Here to get the number of neutron, A minus Z, so this will be 2 minus 1, which is equals to 1. And the third one, to get the number of neutron, that is also A minus Z. So 3 minus 1 equals to 2. To find the number of the protons, that is equals to Z. So it is 1 here. To find the number of proton, that is equals to Z1. And to find the number of proton, Z equals 1. And what about electron? Because they all are neutral, so they will have equal number of protons and electrons. That's why all will have 1 electron. So what is the definition? These all atoms, because they have the same number of the protons, but they have different number of the neutron, we call them as isotopes. So isotopes are atoms of the same element with a different number of neutrons, or we can say same proton number but different nucleon number or mass number. We call them as isotopes. Then these isotopes can be non-radioactive. The isotopes, atoms which are having a same number of proton and different number of neutrons, these isotopes can be a non-radioactive or they might be radioactive. So non-radioactive isotopes does not emit out any radiation. And radioactive isotopes, they emit out radiations. And what kind of radiation they can emit out? There are 3 types of radiation which a radioactive isotopes can release or can emit out, known as alpha. Later, the second part of this chapter, we will discuss in detail these radiation. One is called alpha, denoted by a Greek alphabet. This is a Greek alphabet. Then it is a beta. And the third one is gamma. So if an isotope is radioactive, it might emit out radiation. And what are the radiation it might emit out? There are only three types of radiation which an isotope can emit out. One is called alpha, another one is the beta, and the third one is gamma. About the radioactive isotopes, we will discuss in detail the second part of this chapter. So always remember, whenever we have isotopes, isotope might be radioactive or may not be radioactive. If it is not radioactive, it does not emit out harmful radiation. But if it is a radioactive, it might emit out alpha, beta, or gamma. And there is a possibility it might emit out all three of them, maybe two of them, maybe one of them frequently. But it will be there, like these radiations will be there when the isotope is radioactive. Then about the structure of an atom, the nuclear atom and the radioactivity, Rutherford was the one who explained the structure of an atom. So what was the arrangement by the Rutherford? What he did, this is known as a Rutherford experiment, Rutherford nuclear experiment to find the structure of an atom. What he did in his experiment, he took a gold foil, a metal foil which is made up of gold, a thin gold foil, and he target this gold foil by alpha particles, radiation known as alpha particles. What we observe, he observed most of the radiations are able to pass through. Few of them radiation deflected, like changes the direction, and few of the radiation bounce back. This is what he observed. And from his observation, like this is a Rutherford experiment, what he did, he take a metal foil, a gold foil. So this is a metal foil. And what he did, he target this metal foil by alpha particles. So when he target this gold foil by alpha particle, what he observed most of the alpha particles are able to pass through. Few of them changes their direction and few of them bounce back. This is what he observed. And with this observation, he conclude, there are conclusions. So what are the conclusion? What he concluded, he said, if everything is made up of the particle atoms, so the first conclusion what he drew, like this is an atom of the gold, most of the alpha particles are able to pass through. So this is on the left hand side is an observation, what he observed. And on the right hand side his conclusion, what he conclude. So what he see, the first thing he sees that most of the alpha particles pass through. So what he said, if the most of the alpha particle pass through, he said that because most of these particles are able to go through easily through an atom, so he said that major portion of the atom is empty. That's why most of the radiation, most of the alpha particles are able to pass through, because if nothing is there to stop them, that's why they are able to penetrate or they're able to pass through. So major portion of the atom is empty, or he said that nucleus is very small compared to atom. Like the central part of a atom, the nucleus is very small. Otherwise, if nucleus was big, like example, if this nucleus was big enough, then it should be able to stop these alpha particles. But because the nucleus is very small, That's why the nucleus is not able to stop these alpha particles, and most of the alpha particles are able to pass through the atom. So this is the first conclusion which he drew from his first observation. The second one, the second observation and the conclusion he drew. What was the second observation? Second thing he observed, few of the alpha particle changes the direction when they are moving. He observed few of the alpha particle changes their way, changes the direction. Like alpha particle is moving, it changes the direction, or moving, it changes the direction. So what is the reason for that? First, this is the observation, few alpha particle change deflected. So what he suggests for this, he said that the nucleus, because alpha particles, why they are changing the direction, it means alpha particles are repelled. There is a repulsion between the alpha particle and the nucleus. Otherwise, if alpha particles are attracted, then these alpha particles should move towards the nucleus, but they are repelled. That's why they're moving away from the nucleus. So what he suggests from this, he suggests that nucleus contain charged particles, and the charge on the nucleus is same like alpha particles, because they repel each other. So that is the second thing, second conclusion he drew from the observation. The second thing what he observed, that few of the alpha particles are deflected. If few of the alpha particles are deflected, it means there's a repulsion. And what he suggests the alpha particle and the nucleus have the same charge. Why he said like this? Because if they were having the identical charge, then alpha particle should move to, if they were having a different charge, because unlike charges attract each other, and like charges, when we have identical or same charges, they will repel, and when we have unlike charges, they will attract. So because they are repelling each other, there's a repulsion between the nucleus and the alpha particle. So he said that the charge on the alpha particle is same like the charge of the nucleus. That's why they're repelling, and due to the repulsion, the alpha particle changes the direction. So this is the second observation and the conclusion. And what about the third one? The observation and the conclusion. So we have, what is the third observation? He observed few of the alpha particle bounce back. So if the few of the alpha particle bounce back, so some of the alpha particle might collide with the nucleus and they bounce back. So what he suggests for this, because if anything is made up of matter particles, then only, like example, if I throw a ball towards the ball will bounce back, because of when the ball hits the wall, the particle will interact, and that particle force the ball to bounce back. So same thing he suggests, that why some of the alpha particle bounce back. He said mass or matter is present inside the nucleus which cause alpha particles to bounce back. So there is a mass or a matter present inside the nucleus, and because of this matter, the alpha particles are able to bounce back. So this is a third conclusion which he drew, that he suggests that when these alpha particles collide with a nucleus, when they collide, they changes the direction and bounce back. So these are the three observation, and related to observation, the conclusion from Rutherford experiment. So what was the first, what he said, there are like, if sometime they asked to complete the path of these alpha particles when it is passing. So if the alpha particles are passing away from the nucleus, they will pass straight because major portion of the atom is empty. If the alpha particle is coming closer to the nucleus, it will deviate or it will change the direction. And if alpha particle is coming directly towards the nucleus, it will bounce back. So this is what happened. The first one, major portion of the atom is empty. That's why most of the alpha particle passes through. The second one, because the nucleus contains the charge and that like charges repel, so alpha particle deviate or changes the direction. And the third one, the nucleus contain a matter, or there is a matter inside the nucleus that cause the alpha particles to bounce back when they strike the nucleus. So this is the Rutherford experiment, scattering experiment. So you have to learn the observations as well as conclusion. So the Rutherford experiment, as you can see here, this is a figure which is representing, look, A is closer to the nucleus, so it deviate, repulsion. B is also closer to nucleus, deviation. C and D passes straight, and C passes straight, D close to the nucleus, so it will bounce back. So you should be able to complete the path for the alpha particles when they are passing through a nucleus of an atom. So this was topic 5.1, which is about the nuclear atom. So the question 37 is related to the scattering of alpha particle by a thin metal foil. Like we have a metal foil, the gold foil experiment we just did, that when we pass the alpha particles through the metal foil, the gold foil, what we observe? We observe most of them are able to penetrate or pass through. Few of them are deflected and few of them are bounced back or changes the direction. So the question is, why alpha particles are used rather than a neutron? Like why we don't use neutron? Why alpha particles were used there? Because they always travel more slowly. That is not the reason. Alpha particle, because neutrons are neutral particles. Because if we use neutron, we cannot identify the charge on the nucleus. Because example, this is an atom and there is a nucleus of an atom, and we use a neutron. Neutrons are neutral particles, so even all the neutrons will be able to pass through. Why? Because they are neutral, so they are not affected by the nucleus. So the main reason why we use alpha particles rather than the neutron, so because they all travel slow, that's wrong. Not about heavy, not about the large diameter. So what is the main purpose? The main purpose, because they have charge, because positive charge is there, or they have the charge, because the alpha particles is having a charge, so we can identify the charge on the nucleus. If the alpha particles deviate away, it means they have the same charge as a nucleus. If alpha particle move towards, attracted towards the nucleus, when they are moving, it means they will have the unlike charge. So because the idea is that we should use a charged particle so that when they move closer to the nucleus, either it will be attracted or repelled, and due to the attraction or repulsion we can identify the charge of the nucleus. If neutron was used, then neutron is a neutral particle. Even nucleus is charged or uncharged, the neutron is not affected by the nucleus. Question 38. A nuclide notation for an isotope of silver is given. So what is A here? The nucleon number, that is 109. And what is a proton number? That is 47, or atomic number is 47. How many nucleons are there in the nucleus? Nucleon means the number of the neutron and proton. So the top number A is actually the nucleon number. So how many nucleons are there? So it is containing 109 nucleons. If they ask for number of neutrons, then how to get the number of neutron? That is A minus Z. But they're not asking for number of neutron, they're asking nucleon. Nucleon number means the sum of the neutron and proton. So when we add, the top number is, or the higher number is representing A is representing a nucleon number, where Z is representing a proton number. So the notation of an isotope of a sodium is given. So A is equals to 23 and Z is equals to 11. How many protons are there? So number of the proton is equals to 11. How many electrons will be there? Also 11. And how many neutron? That is A minus Z. So it will be 23 minus 11, which is equals to 12. So it should have 11 protons, 11 electrons and 12 neutrons. So A will be the right answer.